January 30th, 1943, 18,000 feet above the Ruhr Valley, Germany. Flight Lieutenant James Connelly can't see anything. Not the ground, not the target, not even the wingtip of his own Lancaster bomber, through the solid wall of cloud that's swallowed his aircraft whole. Outside the cockpit, the night is absolute. No moon, no stars, just the dim green glow of instruments and the bone-shaking roar of 4 Merlin engines. Somewhere below, 5 miles beneath this frozen soup of water vapor and darkness, lies the Krupp armaments factory in Essen. Somewhere. But somewhere isn't good enough when you're carrying 14,000 pounds of high explosive. Navigator, I need a heading, Connelly calls into the intercom, his breath fogging in the unheated cockpit despite his leather flight jacket and wool liner. In the navigation station behind him, Pilot Officer Thomas Reed hunches over a table no bigger than a school desk, surrounded by charts, protractors, and a device that looks like a small television screen, the H2S ground mapping radar, installed just 3 weeks ago. The screen shows a grainy flickering that might be the Rhine River or might be atmospheric interference. Reed has been trained on this equipment for exactly 6 hours. 6 hours to master a technology that's supposed to revolutionize bombing, to make the impossible possible. Hitting targets you cannot see, through clouds that stretch from 2,000 feet to 20,000, through darkness so complete that visual bombing, the method that's failed 70% of the time for the past 3 years, becomes irrelevant. Come left to 095, Reed says, his voice tight with concentration. Target should be 14 miles. Should be. The uncertainty in those words carries enormous weight. Connelly brings the Lancaster onto the new heading, feeling the aircraft respond sluggishly. She's heavy tonight, loaded with a 4,000-pound cookie blockbuster and clusters of incendiaries. Around him, 19 other bombers from 207 Squadron are navigating through the same cloud, maintaining separation by instrument alone, each one hunting for the same target with equipment most of them barely understand. This is what bombing Germany has become in January 1943. A blind man's gamble played at 200 miles per hour, where success or failure depends on instruments, mathematics, and innovations so new the ink is barely dry on the instruction manuals. It's a far cry from the confident predictions of 1940, when Air Marshal Arthur Harris declared that precision bombing would bring Germany to its knees. Precision. The word has become a bitter joke among bomber crews who know the truth. On a typical raid, only 1 in 3 aircraft comes within 5 miles of the target. 5 miles, in clear weather, with visual S. In clouds like these, the success rate drops to nearly 0. But tonight is different. Tonight, Connelly's Lancaster carries more than bombs. Mounted in the aircraft's belly is the H2S radar, Type 9 Mark I, serial number H2S/1247, a device that weighs 250 pounds, cost more than the bomber carrying it, and represents 3 years of secret development by Britain's top physicists. The name H2S is deliberately cryptic, officially standing for Home Sweet Home, but actually chosen because one scientist declared the earlier failure to develop such radar was stinking like hydrogen sulfide gas. The H2S works by bouncing radio waves off the ground and displaying the return signal on a cathode ray tube. Different surfaces reflect differently. Cities show bright, water shows dark, open countryside shows as gray. In theory, a train operator can identify landmarks, navigate to targets, and guide the bomber to precise release points without ever seeing the ground. in theory. Reed stared at his screen, trying to match the ghostly green shapes to the map on his table. There, that bright return could be Essen's industrial district, dense with metal buildings that reflect rather beautifully. Or it could be Duisburg, 15 miles west, equally industrial, equally bright. The Rhine should help. Water is distinctive on radar, appearing as a dark snake through the bright clutter of urban areas. But the river curves, branches, and Reed's screen shows three dark lines that might be the Rhine, or might be canals, or might be sensor artifacts. Bomb aimer, can you see anything? Connelly asks, knowing the answer. In the nose of the Lancaster, lying prone in the bomb aimer's position, Sergeant Michael Davies peers through the optical bomb sight at absolutely nothing. Solid cloud, skipper. Can't see a bloody thing. This is the fundamental problem that's plagued Bomber Command since the war began. Germany has weather, lots of weather. Cloud cover over the Ruhr Valley averages 7 days out of 10. Winter brings solid overcast that can last for weeks. Strategic targets, factories, rail yards, refineries, sit beneath this protective blanket, effectively invisible to bombers designed for visual targeting. The Northern Bomb Sight, that marvel of American engineering that can supposedly drop a bomb in a pickle barrel from 20,000 feet, is useless when you can't see the pickle barrel, or the factory, or the city. The RAF tried everything. They tried bombing by dead reckoning, navigation by compass and clock, and hit the wrong cities. They tried Pathfinder aircraft dropping flares to mark targets, but flares are visible points, and there are none in solid cloud. They tried radio navigation beams, but the Germans learned to jam or spoof them, sending bombers to empty fields. By late 1942, the awful truth was undeniable. Bomber Command was losing the war of accuracy. Germans were producing more tanks, more aircraft, more ammunition, despite thousands of tons of British bombs, because those bombs were falling everywhere except on the factories. Then came the mathematicians. Professor Patrick Blackett, physicist, Nobel Prize winner, and the most unlikely military advisor in British service, didn't look like someone who would revolutionize warfare. At 45, he was balding, bespectacled, and spoke in the measured cadence of Cambridge lecture halls. But in 1942, Blackett brought something to the bombing campaign that it desperately needed: operational research. Not guesswork, not doctrine, mathematics. Blackett's approach was revolutionary in its simplicity. Treat bombing as a problem in physics and statistics. Measure everything. Test everything. Prove what works and discard what doesn't, regardless of what doctrine says should work. His team analyzed thousands of bombing photographs, calculated actual accuracy rates, measured the relationship between bombing altitude, wind speed, visibility, and success. The results were devastating. The report Blackett delivered to Bomber Command headquarters in October 1942 read like an indictment. Visual bombing from 15,000 feet in clear conditions achieved an average error of 1,200 yards, nearly 3/4 of a mile from the aiming point. In cloudy conditions, that error increased to 5 miles. 5 miles. At that distance, a bomber aiming for a ball-bearing factory was as likely to hit a residential neighborhood, a park, or open farmland. The conclusion was mathematical and brutal. Without fundamental changes in targeting methods, Bomber Command could drop bombs on Germany for a decade without significantly impacting industrial production. But Blackett didn't just identify the problem. He identified the solution, and it lay in a technology that most senior officers barely understood: centimetric radar. The H2S radar represented a breakthrough in microwave technology, operating at 10 centimeters wavelength instead of the meter-long waves of earlier systems. Those shorter waves could map ground features with resolution measured in yards instead of miles. More importantly, they could penetrate clouds. Radio waves don't care about water vapor. They pass through fog and overcast as if the weather doesn't exist, bounce off the ground, and return with information about what's down there. The challenge wasn't building the radar. British physicists at the Telecommunications Research Establishment had cracked that problem by early 1942. The challenge was turning radar returns, blurry, ambiguous, flickering S on a small screen, into actionable bombing data. That required tables, thousands of tables. Bombing tables that accounted for altitude, airspeed, wind speed, wind direction, bomb ballistics, temperature, air pressure, and the relationship between radar and actual ground distance. Blackett's operational research team spent 6 months creating those tables. They flew test missions over Britain, comparing radar images to known landmarks. They measured how different features appeared on H2S screens: cities, bright; rivers, dark; coastlines, stark contrast; railways, linear features; forests, medium gray. They calculated the geometric distortion inherent in looking at the ground from a moving aircraft at an angle. They factored in the Earth's curvature at extreme ranges. They produced bombing tables that told navigators, if you see this pattern on your screen, at this altitude, at this speed, release your bombs this many seconds before the target marker crosses the center of your display. It was mathematics translated into warfare. Differential equations became bomb trajectories. Statistics became targeting decisions. And in January 1943, the first H2S-equipped Lancasters began flying operational missions over Germany, carrying not just bombs, but the accumulated knowledge of Britain's finest scientific minds.